Now, let's find the limit of 1 over x squared when x approaches 0. Well, we cannot do it right away. We need to figure out left and right limit. Let's do left limit first. 0 from the left. And then after that, let's do 1 over x squared. This is 1. X approaches 0 from the right. Like so. And just as before, you imagine this is your x-axis. X approaches from the left. At the same time, output approaches from the left, but on the graph. So the height is keep going, keep going, keep going. And apparently it can keep going up forever. What would you say about that? Infinity. Infinity and plus infinity is the same thing. So let's write down plus infinity, but you will see that in mathematics we don't distinguish those two. So plus infinity, and then I will write down for a couple times up. Up forever. So let me do up. But again, it's not x going to infinity. Output is going up forever. What do you think happens from the right? X approaches from the right to 0. I will put a pencil from the right. While x approaches 0, output goes also up, exactly, to positive infinity. Up. Maybe you recognize, maybe not, it's fine, we'll be recovering all this information, but whatever in between, x equals to 0, is vertical asymptote. X equals to 0 is VA. I'll write down definition in a second. VA and HA, very convenient ways to write down vertical asymptote and horizontal asymptote. Usually it's dashed. Something dashed means that it is important or you cannot reach it. But usually something is important happening, then it's dashed. Sometimes you can actually reach it. Now, conclusion. What is happening? Let me change the color to... At some point I should ask you what colors do you like. Oh, wow, that's very thick. So what is happening at the limit of 1 over x squared? X approaches 0. You'll be surprised, but American books did not agree on that. Some American books of calculus saying, we should say does not exist because plus infinity is undefined. That is true. F of x, no, f at 0 is not defined. It's not in a domain. There is nothing to have as an output as f at 0. Or you can say it's infinity. And this is when people do not agree. Should we say it's not defined or should we say it's infinity? Is infinity means defined or not? So in this class, we will say if they match, we will be consistent with what we know before. Left limit and right limit approaches to the same thing. Just not now this thing is not a number. It's infinity. Then they both meet at infinity, which is pretty cool concept to think about. That they will meet, but at infinity. Infinity and beyond. Which is actually not correct. Mathematicians always fix this phrase from the Toy Story. We say beyond to infinity. So infinity is the last thing, not the beyond. Do you know what beyond of the infinity? More infinity. So they meet in infinity. And actually some upper level math with proofs goes to complex analysis and imaginary numbers and so on. And they do work with where parallel lines meet and where dividing by 0 is okay or square root of -1 is fine. So they do talk about those things. In this class, let's remember if they meet, basically go the same way, then you just say, yeah, they're equal to each other, conclusion, it's plus infinity. Does that make sense? There's one more way to justify it. Before I move on, probably last time I should just show you this idea. I was thinking about for a couple of classes if I should show you or not. On the board. Just one more time. X approaches 0 from the left. Maybe never gonna reach it. It's not defined 0, but it points it. At the same time, I'm gonna put a marker. F of x is working simultaneously. Output depends on the input. So this is very important to understand that they grow or move together. They don't exist without each other. So output goes up, input goes to 0. That's the idea. Sometimes we're gonna ask you, okay, there's a vertical asymptote, but where? Then it's about input. Where means x-axis. Yes?
Can we say that these lines never get vertical or like parallel to the y-axis?
Oh, very clever. So we're gonna make a definition right now. They will never reach it. So vertical asymptote has a cool feature that they will never reach the complete vertical state. They'll be still tilting a little bit. It will be almost vertical, but if I zoom in a lot, it's still going to be a little bit tilted. So going there, but you remember the limiting position means might never reach it. That's the idea. Let's talk about from numerical sense. You don't have to copy this. It's in my notes. Sometimes you can check it with your calculator. If you're stuck on the test or exam, algebraically is doing this to actually figuring out what is happening with 0 when you plug it into denominator. And I'll show it to you in a second. But numerically, you can also figure out when x approaches 0 from the left, I can plug minus 0.0. Again, don't have to copy this. Minus 0.01, 0.001, 0.001. All very small numbers, but negative. But very small, very close to 0. The output are what? Small or large? Large. Positive or negative? Positive. Are they getting smaller or larger? And they're still positive. Larger. Large, right? So, I guess, let's just do huge. I like the word huge. I don't know. It feels like very dramatic. Huge numbers. Huge, and then let's do numbers. But it's important they're huge and positive. Negative infinity, we call huge numbers, but negative. So that makes sense. They're still huge, but negative. So huge numbers. Make a circle, yeah. Numbers and positive. So that's how you can check. How about x approaches 0 from the right? I'm going to plug 0.01, 0.001, 0.001. They are still getting huger, bigger and bigger and bigger, and positive. So that means they go to infinity. But by they going to infinity, that's what it will take you time to get used to. This is the official notation. If you don't want to, some people don't write limits. They write down this idea. F of x goes to infinity. Plus infinity, infinity is the same thing, so you can drop the plus. As x approaches 0 from both sides. That is the same thing as the limit of f of x equals infinity as x approaches 0. I would say thus. Numerical way is not the best one because sometimes functions do something crazy at the very last moment. So algebraically is better because then you definitely can prove based on properties, laws of limits, the table you saw, that indeed that is what's happening around 0. Definition. I'll show you cool animations. I collected animations yesterday. So let me show you a couple definitions first. This is what you need to remember. I mean, it's not like I need you to remember the words part of definition. But when we ask you find vertical, horizontal as on the test, and we will ask you this on the final exam as well, and in calculus 2 and in calculus 3. So it will be there everywhere. So remember it as early as possible. You need to remember this idea. If they ask you about VA, so let me do, once I will write it down, vertical asymptotes. That's correct, asymptotes. Totes McDotes. That's what my American roommate taught me to say. Totes McDotes. Do you know what it means? I don't know. I sometimes I say this weird American phrases because someone taught me them. VA. I like calling it VA. Don't confuse it with veteran affairs. That is a system of hospitals. So let's write it down. We have limit. The definition is f of x gives you. So this is an interesting thing. X approaches a number. X approaches a number. Let's go with A. From left, from the right, whatever. But the output is infinity. Plus or minus infinity. That's the cool thing. So that's why it's unusual. Asymptote is an unusual case because input approaches a number. What is my profit in January 5, January 6, January 7? But the output suddenly is infinity. That means either you have a mistake and you should fix it. Maybe some equation have division by 0 and it was wrong. Or some kind of unusual behavior happens. Why there's suddenly in the space, the closer you approach something, the more huge numbers show up. And that's how they detect it. Black holes, it's lights being reflected and so on. But that's literally how limits work. So definitely the space signs is the rocket science. It's full of limits. We write down this phrase. We can make, why it's so fat today? We can make f of x. Before it was arbitrary close to some number, but this time it will be arbitrary RB2. Do you remember what arbitrary means? Nearly but not exactly. I like it. Nearly but not exactly. Arbitrary. It's like close enough. Also, that's how I like it. Arbitrary, large. Large. It's weird. So large is plus infinity, so you can ask how about negative infinity. Well, that's what I told you. We decided to work with it as large and positive or large and negative. Then it kind of covers both infinities. I like this idea. We don't redefine something new. We still use large numbers, but just positive or negative. As, so for all x that are close to a from both sides. From both sides. From both sides. But also x cannot be a. It's not defined. What do you mean from both sides? But what if it's only from one side? What if from the left it goes up and from the right it goes down? Or what if from the left it goes up and from the right it just stops? We have cases like this. Piecewise functions can do whatever you want. That will be cases of side limits. So we're gonna write down, let me change the color to like this one. If you wanna work with limits f of x that give you, I will write down plus and minus infinity, it's just easier, plus and minus infinity, but x approaches a from the right, and then x approaches a from the left, so that's the only difference. So I put it one below another one, that means or, but actually multivariable calculus we're gonna have 5 variables over there in limit and derivatives and stuff. So that's only from one side. So side infinite limits. So those are infinite limits because the output is infinity. Then the question, so let me show you the picture and ask you a question. This is the example. Do you know a classical example of when one side goes up and another side goes down? I already mentioned it. 1 over x. Did you think about 1 over x? I thought about it at the very beginning. That's a classical example. Actually, 1 over x is a pretty troublemaking function. I will show you later. It has connection with a logarithmic function, so it's very interesting case. It always have a troublemaking situations. So it has 2 asymptotes, vertical and horizontal, looks like that. But my idea is from the left around 0, limit goes where? Plus or minus? Minus. It goes down. Exactly. Goes down to minus infinity. From the right, it goes up like before to plus infinity. So the question is, let me write down, then limit as x approaches a, not from the left and not from the right. Not a, in this case it's 0. What do we agree to write down? And again, this is where books do not agree. So, yeah, the books will say, I saw different things, so I was asking people around, and they said, okay, just follow the book we have here. So in this book, we're going to follow the same idea. They did not meet, guess what? Does not exist. Does not exist. So that's the good news, that you don't have to learn anything new. They did not meet, they're not friends. In this case, they're actually infinitely not friends. They're going away from each other forever. So that is a vertical asymptote. But that doesn't really help me how to find it. That's a nice definition. I like it. It looks beautiful. Let me put it in nice, beautiful yellow color. But it doesn't help me how to find it. So recommendation on how to find it, let me put right in front of it. Oops, let me do it like so. Dot, dot. To find it, someone mentioned, check the denominator. So in this case, at 0, it was 1 over x squared, 1 over x. Also check the denominator. Where is denominator? 0. So check denominator is 0. That is not only the case. If denominator is 0, it's not always vertical asymptote. Might be a whole, but you just check it. Check denominator to be 0, and then it pops out if it's there. At x, oh no, it doesn't have to. Just check denominator 0. So that's all you need to do to find VA. We're going to do so many examples, so you will feel confident with VAs. Horizontal asymptotes, somehow students don't like it, but I actually feel like they're easier than VAs. So let's do definition. Yes?
If the infinities don't meet like in 1 by x, then the limit is like this.
They don't, if infinities don't meet, then D and E.
If they are pointing at different infinities.
Yeah, then we say D and E. So, yeah, basically the same we had before. Left limit did not meet right limit.
Right.
We say that the limit does not exist. HA, horizontal asymptotes. Did you know that the word asymptotes has Y in it? It took me forever to remember that. At the very beginning when I was teaching, I wanted to somehow have a shortcut for asymptotes because it's hard to write down. So I would do AS, and then something clicked in my mind, and I remembered it has double S, so you will not believe, but I would leave it like this. Took me like 2 weeks to realize that that is not right, and nobody said anything. Students are too polite to fix people. So that is not true. It's ASYM, okay? Asymptotes. I will call them HA. Yes?
Is that a standard notation, VA and...
So in America, yeah. Around the world, no.
Oh.
Around the world, they don't use English necessarily, right? So vertical asymptote is вертикальная асимптота. Still VA, but it's going to be different VA. And горизонтальная асимптота has G in it, so it will be like GA. So no, we all have different notations. But in America, they do, and I really liked it. It's kind of very fun and short. That one is easier. You just set, to find it, let's do ... You set, if you have a fraction, limit for x to go to plus and minus infinity, and see what happens. So just send the limit to go far away to the left or far away to the right, and see what's going to happen. So let's write down the definition. I would put it like to the right somewhere here. Set limit as x goes to plus or minus infinity, and see what happens. But the definition is, when x goes to plus or minus infinity, you assume like, okay, probably it always gives you infinity. That is dot asymptote. But then somehow it's a number. How weird. So x is growing forever. Say 1 year, 2 year, million years, billion years. And the answer is still 5? That is odd. And that's why horizontal asymptote is a cool, unique case, just like vertical asymptote. The answer is a number. So with the vertical asymptote, x approaches a number and the output is infinity. That is rare and cool. And here's the other way around. X goes to super far to the right or super far to the left, and the answer is a number. All the time it's 5 or 5.1 or 5.1 or 5.51 and so on. That is weird. So that's horizontal asymptote. Basically, the output stacks around a number. So let me write this down. I like this way, the way I explain it, so let me just write this. This is a whole definition, to be honest. So while x is huge, and remember, huge, positive or negative, right? Both huge. Let me write down positive. Let me write down positive or negative. Don't do that. Positive or negative. Let me know if whatever I said writing down does not make sense. Especially people at the back, let me know. But f of x is getting closer and closer, as close as we want, goes to a number, approaches a number. That's how cool it is. So that is a pretty also interesting case. There's so many applications on those things. Lots of them. Biology has lots of horizontal asymptotes, which is also pretty cool. So we're going to be doing it right now in different examples. But I wanted to show you first some animations. Do you have questions? Yeah?
Ma'am, can't we change the coordinates in the vertical asymptote to make it horizontal?
Can vertical asymptote become horizontal?
Yeah, change the coordinates.
Yeah, you can, but we don't usually do it. So the question is if we can flip x and y axis. Yeah, people do it, but we do it sometimes in calculus 3, actually. Yeah, we're gonna get there, but not soon. But you will see it in probably engineering a lot. Yeah, it's a good question. So horizontal asymptote, I can illustrate it this if you want. Here it is with the same function. While x is going to the right, f of x is shrinking to 0. That's HA. We're going to write it down in a second. So let me show you those beautiful animations I found. What is that? Vertical asymptote. X approaches A from the left and from the right. F of x gets crazy. So left limit goes where? Down. That's correct, down, and that's correct, to negative infinity. And the right limit goes to plus infinity. So limit at the point does not exist because it did not meet. So classical, this nice example. Now I have this one. Look at this, how beautiful it is. That one is my favorite. It's a very good representation. What happens at A? Vertical asymptote. Do you know that it has horizontal asymptote too? Yeah. It does. If you look horizontally, they just don't talk about it in this case, but it has it. So this case has both. It's still 1 over x. It's just shifted again. Vertical and horizontal asymptote. And again, one goes down, one goes up. You see they color-coded. The cooler part of this animation is this is a complicated concept, and you don't have to understand completely, but it's super fun to mention it. Functions are continuous. That means if I change a little bit input, output will also change a little bit. Functions can jump around, but it's not like I change input by 0.1 and output is 1 billion suddenly. Such a gaps, jumps, usually indicate some kind of irregularity, so discontinuity. The input was at 5, and then suddenly the next step, input is at the billion. That's probably a jump, or a horizontal asymptote. In a horizontal asymptote, and I will show it to you, pencil, and I'll show it to you on the board. When x approaches A, a little bit of input, output is not very different. That's what they show here. A little bit of new input, not very different, not very different, not very different. A little bit here, and it drops down. So that is an indication of something unusual. In this case, vertical asymptote might be jump. Maybe it's stuck here, and then the next point is minus 1 billion. So that indicates some kind of discontinuity or unusual behavior. Again, you see, it's slowly going. When I'm changing a little bit x, y is a little bit changing. But over here, see, it's keep going, right? Over here, tiny change in x drops down to who knows where. It's not even on the screen, in height. And on the right, little change here suddenly goes super high. So we were going to talk about exponential functions. They tend to have behavior like this. That's why rocket, when it goes to the space, have behaviors like this. It slowly accelerates and at some point just goes up. But still, vertical asymptote will be like super speed, faster than speed of light. Those kind of behaviors. So we talk about those things. And explosions, my favorite, of course. Little bit of extra chemical and suddenly blows up. And that's why at A, you're not defined because you're dead. That's the idea. So I always like mentioning that. Kind of dramatic. Now, horizontal asymptotes. Check this out. So x is input, goes to plus or minus infinity. Output stuck around the number. On the right, they stuck at around number L. On the left, output stuck around number M. They might never reach it, but they stuck around it, and they get closer and closer to it. Basically, think about that a function the output, tries to hug an asymptote, vertical or horizontal. It tries to hug it, but it might never happen. So with this one, it's pretty cool because this is the limits that will help us to go to the future and the past. What happens with the Earth in 10 years, 100 years, 1 billion years, that x goes to plus infinity. And actually the model's telling you what happens with populations of animals, the lakes, and so on. The lake, so the waters keep accumulating in the lake. Will it be infinitely big lake? No, it will have an asymptote. It will reach some kind of limit and stuck there if it's not going to evaporate. So there's lots of cool examples on that. Or I like to talk about exponential growth. If I have a guppy fish in my aquarium, and I do, and they reproduce like crazy, they have 55 babies every time, and they get pregnant every 3 days. So when I had them, they start overpopulating my aquarium. So usually you buy a predator. If you buy a predator, they eat only the babies when they're born. Also, guppy fish, they born like live babies, not eggs. So like they just blew up with 50 babies. It's crazy. This tiny fish. So very sad fortune, to be honest, to be a female guppy fish. That's what they used for experiments too, just like zebrafish, because they reproduce fast. So if I would not buy the predator that's regulated my aquarium, does it mean that at x goes to infinity, so 1 week, 2 weeks, 1 month, 12 years, I will have infinitely many fish? No. Do you know why? What? The dice? No, I feed them. I'm not a monster. I feed everyone. Dice starving.
Not as much space in the aquarium.
Space in the aquarium, right? How do you also call it? Environment restrictions, right? Yeah, they will be dying, but still there will be more people there. Anyway, so there's some kind of restriction, so it's not going to be infinity at infinity. They will stuck around number L, for example, some kind of limit, and they will stop reproducing. That's nature, so it makes sense. Natural restrictions. So those examples are classical examples. These kind of things here, this is the faster idea. So do you know that cells in your body talk to each other? It was proven like 20 years ago, pretty recent, but still. The cells of your skin, why our hands have the same lengths. Actually, there's a mathematical model explaining that. The brain tells you when to stop to grow hands, and left and right, it's pretty complicated. They don't grow outside of each other. So cells outside of, at the edge of the skin also talk to each other. The cell at the very outside see the end of the space, and they stop dividing, and they give a signal back saying stop dividing, we hit the edge, and then it goes back, stop dividing, we hit the edge, and then it says slow down, we're hitting the edge, and then it says please slow down. So cells talk to each other, and that's why you don't overgrow things, except the crazy cells, which grow for no reason. Do you know the name of those cells?
Cancer.
Freaking cancer cells. The whole point of the mutation, they stop talking or understanding the language. Either they send the signal and cancer cells do not receive them and they keep dividing and a tumor shows up, or they just don't say anything and they keep dividing forever. And that's what the research is about, to figure out that. Those cases sometimes called steady state, but as you can see, horizontal asymptote can be crossed. Vertical asymptote will never be crossed. The function is not defined at 0 for 1 over x. There's nothing can happen at 0. It's not going to cross it. But for horizontal, it's a long-term behavior. That's a terminology. Long-term behavior. So it might cross it many, many times, maybe a lot, and then stabilizes. So if you only do research on this part from 0 to 10, you think it's just random. That's why do research maybe till 15, till 20, till 100, till infinity. At infinity, you see it stuck around the number. So that's also a pretty cool example. And everything, there's a page I found. They have lots of cool stuff there. Isn't it cool?
Do we see the previous animation that it was horizontal asymptote?
Yeah, there was this one, see? I think you meant this one. That one is horizontal. This one?
Yes.
Yeah. So if it reaches it, it's not horizontal asymptote, but if it keeps oscillating forever around it, it is. That makes sense? So it will be like jumping around it forever. That's a horizontal asymptote, even though it's keep crossing it. That's the difference between horizontal and vertical. And these guys, you see, you can change the asymptote. Look at that. Vertical, horizontal, I keep changing. Well, you are the one who's changing them, using those coefficients in the fraction. And right now I'm going to teach you why that matters. This is what we're going to be doing right now. We're going to find asymptotes. But in this case, you know the asymptotes and you change them using the coefficients. So that's also data science, because you can collect data and see what's the difference between results, and then you can manipulate those results to change the data. So that's kind of data analysis also. There's lots of stuff happening with asymptotes. Look at it, how cool is that? Let me close it to have more time. Okay, let's continue with examples, because I think you need to figure out how to work with stuff. Work with limits. Let me put a line. So basically, let's learn how to work with limits. It's not an official name, I just made it up. Let's work with limits. What kind of limits? Infinite limits or limits at infinity. That's what we just learned. This is the idea. I'm gonna show you the long, annoying way and then short, fascinating way. So 2 ways to do it. Way 1. In the book, you will see they say divide both numerator and denominator. Numerator and denominator. Do you know by what? By the highest power of x. Power of x. And that's what you're going to see in the book, so I want to show you that. I never do that. And I will tell you, most of you will never do that either, because I will teach you how to skip that in the domain. But I need you to understand what they're doing. Just like when I saw it for the first time before teaching, I had to understand what is going on. Example. Yes?
Is it the highest power in the domain or?
So I'll show you right now. Yeah. Limit 3x to the 5 minus 4x squared plus 3x minus 10 all over minus 10x to the 5 plus 3x minus 1500. X approaches infinity. So that's an infinite limit. So are we going to plug infinities? No. We're going to do it, but later. So the book says you plug infinity, you don't know what's happening. In this case, it's like infinity over infinity case. So the book says let's divide both numerator and denominator by the highest power, like in the song, the highest power of x. That means let's find the highest power of x from both sides. Which one, the highest power?
5.
X to the 5, exactly, 5. So they're the same, doesn't matter. So find the highest one, you don't have to do both. Just one highest is good enough. And divide everything by that power. So we're gonna do that. Let me make a note that I'm dividing, that's like divide by x to the 5. By the highest power of x. It's not by 5, by x to the 5. And then this, like the annoying process starts when you need to be careful with details. I will skip a step. My notes, I did not skip it, but let me know if you don't get it. When you divide by x5, you divide each term by x to the 5, right? So 3x to the 5 over x to the 5 is 3 minus, let me spell it out loud. 4x squared over x to the 5 is, I guess, probably should write down because I see like people will not have good notes. 3 times 1 minus 4x squared x to the 5 plus 3x over x to the 5 minus 10 over x to the 5. I just realized that. Probably should write down everything. So you have good notes. Minus 10 times 1, I don't write down x to the 5 over x to the 5, we know that one, plus 3x over x to the 5 minus 1500 over x to the 5. This is what you get. So I just divide it. Here they are, here they are, here they are. And then you use lecture 0. If you missed it, watch it, which the one I gave, when we reviewed how to work with exponents. You basically subtract the power at the top and the power at the bottom. So 3 minus 4, x squared and x5 gives you x to the minus 2. We can write down as minus 2, or we can write down 1 over x squared.
Is it minus 2?
3, right? 1 minus x cubed. So 1 over x cubed will be better, trust me, right now. 1 over x cubed. Plus 3, x over x to the 5 will be 1 over x to the 4. Minus 10, let me do over, 10 over x to the 5. Nothing cancels out, it's a constant. So also I had to say, don't do slash x to the 5. You have bad habit from school, some of you. To the slash, you will, in this chapter, you will have problems, I think. I saw it so many times with a slash. I'll show you in a second why. It's visually nice when something at the top and something is at the bottom for infinities. So try to stop using the slash part. Don't do that. Minus 10 plus 3 over x to the 4, yes, and minus 1500 over x to the 5. Oh, it took forever. Okay, this is the idea. Now we're gonna plug infinity. That's gonna be cool. So I'm plugging infinity. Remember, step 1, plug in, did not work. Step 2, simplify. So we factored out thing. Step 3, plug again and hope for the best. So when we plug to the infinity, 3 doesn't move anywhere. So 3 at infinity is still 3, because there's no x there. But what is happening with minus 4 over x cubed at infinity? Yes. Shrinks to 0. Not only we just saw it here, what is happening over here? As x approaches infinity, 1 over x approaches to 0. Okay, we have that, but in this case it's 1 over cube. Still, you can use your calculator to figure it out, but that's not how I'm doing it. X at the 100, 1 over x cubed will be small. It will be 1 over 100 and more 2 zeros and more 2 zeros, right? Then 1 over, as x is a billion, it will be smaller and smaller and smaller. Shrinks to 0. And a justification of that, the way I teach, it's kind of fun way, but students remember it better. When you divide, so leave some space. So idea, I will explain it right away. So let's say a is a number. Now we can do n, I guess. N is a number, just a constant, right? If you have n over infinity, you divide by the biggest numbers you know, you get the smallest number you know, which is 0. That's how it's easy to remember that. 1 over x to the 17 gives you 0 at infinity. Make sense? But again, we don't divide by infinity. It's just a mnemonic way to remember. You divide by the biggest number, you get the smallest number. So all of these guys, they don't cancel out. They go to zeros, zeros, zeros. This guy, go away. This guy, go away. Usually people don't circle them. They just show these arrows. In the American style, it's like crossing, like so. Go to 0. And then write down the answer. Limit is already gone because I already applied the limit. The answer will be 3 at the top. The only guy that did not go to 0 because it's constant. Minus 10. Same thing. Minus 3/10. That is the answer. Does this function, which is a whole fraction polynomial has a vertical or horizontal asymptote? Do you know? Yes, I saw some people noting. Which one does it have? Horizontal. At infinity, it did not give you infinity. Usually like parabolas growing forever, cubic function growing or decaying forever. This guy stuck at minus 3/10. That is horizontal asymptote. Notation is HA, and that is height stuck. Y equals 3 over, well, minus 3/10. So it's Y, because height stuck around minus 3/10. That's the idea here. So let me show you other things to remember. So dividing by the biggest numbers, positive or negative, gives you positive or negative 0, but it's still 0. Put it in the box. I should put it in the pretty box. The next pretty box will be a little bit more complicated. If I have a number divided by 0, oh, but we cannot divide by 0. But remember, we're approaching 0. So it's a limit. So it's fine. That's why I say in Calculus 1 in college, we suddenly start dividing by 0, freaking all the time. Because we introduce limiting positions, it becomes legal. So dividing by the smallest number you know gives you what? Infinity. The biggest numbers ever are infinity. That makes sense. Divide by 0.000001, it gives you 1 million, 10 millions, 5 millions, right? That makes sense. So we're gonna have plus or minus infinity. Now the sign matters. You'll have to check if it goes to positive or minus negative infinity. Like we had here, the very beginning, 1 over x squared. They both went to plus infinity because when you approach 0 from the left and from the right, input got squared. But 1 over x goes to negative and positive. So you have to carefully check that. Put this in the box. That will be important. Finally, the two cases which are not that important, but I realize people need to know. Put it in a different color maybe. If you have 0 over the number. Okay, 0 over the number is 0. Don't overthink this, okay? That is just makes sense. Then don't overthink this. And if you have infinity over a number, it's also infinity. Like nothing can beat infinity if it's just competing with a number. Then it's plus or minus infinity. The only difference is you need to keep an eye on the sign. Maybe when you divide it by -7, infinity flipped to negative or positive, whatever. So that's the only difference. That's important. And now I'm gonna teach you.
I have a question. It's maybe kind of silly, but what would 0 by 0 evaluate?
0 is what?
0 by 0, what would that?
Oh, 0 over 0 will be the best case. We already learned it from the algebra. You had 0 over 0 in this homework. Algebraically, you had this polynomial or polynomial, and you had to factor it out and cancel it out. H over H kind of things. And then we're gonna learn more. 0 over 0, infinity over infinity are two most interesting cases.
Wouldn't infinity over infinity, yeah, that would be.
And we're gonna have 0 to the 0 raised to the 0. 0 times anything is 0, but anything raised to the 0 is 1, so which one is winning? 0 to the 0 is super cool. Infinity to the infinity is super cool. 1 to the 0, surprisingly, is not obvious either. So we're gonna have cool cases.
1 raised to 0.
Infinity to what?
Over infinity being 1.
Yeah, infinity over infinity is not 1, surprisingly either. Actually, this case is infinity over infinity. Let's check. If you plug infinity right away, 3x to the 5 is infinity. 4x squared is infinity. 3x is infinity. Infinity, infinity. 10 and 15, they do not care about infinities. They just add up. So it's infinity over infinity case, and it was not 1 because of the speed of each infinity. Might be not the same. So one is like nuclear explosion, and the other one is a black hole. They both explode. Well, one actually probably implode, whatever. And we don't know the speed. Of course, black hole will win. So that's why we don't know which one is faster. So I'm going to teach you that right now. Yes?
You said a function can never cross the vertical asymptote if it has one, right?
Yeah.
What if the function is like y equals arcsine of xy?
Arcsine?
Yeah.
Oh, arcsine is interesting. We're going to talk about. We're going to restrict the domain there so it doesn't
Then
cross.
it will cross over, right? And it will also have a vertical asymptote?
No, it will not cross it. We're going to restrict the domain for arcsine. Yeah.
If it restricted domain, it doesn't go further.
Exactly. You can, yeah. We're going to talk about it, I think, in this class or calculus too. Yeah.
But if it was a horizontal asymptote, if we just like switch the axis, it should be vertical asymptote too.
It's still going to be behaviorally speaking horizontal. It's just definition will switch. Limit of input goes to infinity or output is infinity. That's a good question. You should stay after class. I'll tell you what happens if you switch axes.
So in sine inverse of x, it won't cross the vertical asymptote because you can't have values beyond -1 or 1.
Because it's not defined there. That's why.
Yeah, because you can't have, that's why it won't cross it.
Exactly. So for 2 minutes, let me show you how to solve this problem faster. Because literally it takes 2 minutes to solve this problem. Yes, let me make, yes?
What happens if it's not vertical or horizontal? If it's like a diagonal axis?
Very good question.
Those function like, I believe, well, because it's It
Oh.
function like a horizontal asymptote, right?
No. So the question is a very cool question over here. What if it's not vertical, not horizontal? Is it still possible? Sometimes they just give you infinity. And infinity is infinity. That means it's growing forever with no weird behavior. It doesn't have vertical walls and it doesn't stack horizontally. Just keep growing. Like parabola or x equals y or y equals x, right? Grows forever. Like your age kind of grows forever. So this thing can be solved fast. And we're going to do more on Wednesday. In literally longer, I will be talking about it, actually solving. Find the highest power of the numerator. I call it the leader. 3x to the 5 is the leader of the whole polynomial. Trust me, and I'll show you graphically later, everything follows the leader in the polynomial. The highest power rules and defines the behavior. It's like a head of the comet or a snake. I like the comet idea. The denominator, find the leader at the top, find the leader at the bottom, and just kick out everything else. At infinity, only leaders matter. So when you kick everything else, you will have 3x to the 5 over minus 10x to the 5. Cancel out minus 3/10. So the answer will be, and that's the terminology we use, the ratio of the leading coefficients if the powers are the same. And the powers are the same. That takes like 0.5 seconds to solve this problem. While the book tells you to do this division by the highest power, it's so long. So I'll teach you fast tricks on Wednesday, and you'll be solving homework fast, and exam too. I will see you on Wednesday.
What if the powers are the same?
Yeah, that will be very interesting. Then we're going to have 0 or infinity or nothing special.
You can't use this method for the powers are the same.
No, we will. You find the letter at the top and the bottom, and the powers are not the same, and you will get one of those cases.
I know, I was waiting for it.
So it's 5 over 10 x cubed and x squared. Then denominator is infinity, bigger infinity than the numerator. Then the answer is 0. So we're gonna do this on Wednesday. Yeah. So that will be very fun.
Ma'am,
Yes?
you look out the first leader terms and then follow the same process.